Is there an algorithm for truth? This sounds like clickbait or philosophy, but in mathematics, Hilbert's decision problem asks if an algorithm can determine truth. Algorithm means a fixed list of instructions, like a computer program. Statement here means mathematical statement. True here just means we can find a mathematical proof. The Hilbert here is not the Pokemon black and white trainer, but the German mathematician Dave Hilbert. The problem is also known as the Entscheidungsproblem, because it sounds more profound in German. Lots of mathematicians are famous for solving important problems. Hilbert wasn't famous for this, or for silly hats, but for asking important questions. Let's look at some true and false statements. We want statements to include variable assignments, like setting y to 1. We'll use the programmer's double equal to mean an equality test. Y plus 1 is 2, so that test comes out false, so let's put it on the left. A statement like this would be true, so we'll put it on the right. We'll also want to be able to ask questions involving set operations, like there exists a variable x, an element of the set z, which is the set of integers, or Zahlen, such that x times 2 equals 8. Does an integer like that exist? Well, x equals 4. So this is true. How about this one? Now, it's hard to say that an integer, something doesn't exist, but x times 2 has to be even, 5 is odd, so this is false. Now, Hilbert's decision problem asks if we can assign true or false to any statement. Well, how about this statement? It says it's false, so that sounds good to me, but if you agree that it's false, well, then the sentence as a whole is true. And it doesn't help if you flip it around. If the whole sentence is false, then that makes the end of it true. There's just no consistent way to assign true or false to this statement. There's a direct analogy here to logic gates. If you've got a NOT gate, you put in false, you get out true. If you put in true, you get out false. But what happens if I wire the output directly to feed back to the input? Well, there's no statically stable state, and in combinatorial logic circuits, you're just not allowed to do that. Case closed. So for this sentence, the solution in math is simple. We ban it. It's English, it's not math, it sounds like a grade school insult, not something profound, even though people have been thinking about it for thousands of years. So problem solved. So we're only going to look at math statements. Now, here's a math statement. It looks like math, at least. We're defining a set R as the set of all sets X, where X isn't an element of X. So sets that don't contain themselves. We then ask whether R contains R. This is called the Russell set, after Bertrand Russell, the smirking mathematician that created it. So to see how this goes, we don't even know what R contains, so let's assume that R contains R. Now, that means that R doesn't satisfy its own definition, so R can't contain R. That doesn't work. Well, fine, let's assume R doesn't contain R, and see what happens. Well, that means if R doesn't contain R, then it's in R all of a sudden. The problem, again, is that there's no consistent way to evaluate this statement. If you say it's false, it says it's true, and vice versa. The early 1900s solution to this is really simple. Ban it. Russell and several others worked to ban his own set from mathematics, which, along with lots of others that look like this. So you can still have lots of mathematical statements that don't have self-reference that are interesting. So for a couple of years, it seems like this problem was solved, or at least papered over. Then computers came around and made everything harder as usual. We can ask the same question about computer programs, basically just a function and its input, such as JavaScript, and ask the simplest questions, like will the function eventually return and stop, or will it just keep running forever? So this works exactly like classifying math statements. If we look at a function that just returns, that halts. A function that loops forever, it doesn't halt. A function that loops and then returns, this shouldn't be that hard to figure out, it's just JavaScript. But I forgot to increment x here, so this loops forever. If we fix the bug by incrementing x, then this now halts. So the boundary between halting and not halting can be subtle, but if you work away at a program for long enough, it looks like you can usually figure it out. One way to make progress on this problem in general is to rewrite it in more programmer-friendly terms. We're really asking if it's possible to write a function halts that takes another function as an argument and returns whether that function is going to halt. Being concrete about this function halts lets us work with it. So we can build a counterexample. Here's our counterexample. It's this function named arg. It uses the same contradictory self-reference trick that we used for the Russell set. The idea is that if our hypothetical function halt says that we halt, then we're not going to halt. And if the halt says that we don't halt, then we're totally just going to halt. The net result being there's no predicting what this function will do because it will immediately do the opposite of whatever you just predicted. In order to have an orderly division between true and false, it's super tempting to just ban this sort of self-reference. But banning this one is a lot harder than it sounds because the amazing work of these two jokers. Alonzo Church's Lambda calculus is built entirely from one-argument nested functions. You don't need integers, loops, or names for anything, and it's still powerful enough to compute basically anything that you can compute. Here's a tiny little JavaScript function written in the Lambda calculus style to compute the factorial of 10. The first line defines a function that calls the following lines using itself as an argument, which lets it perform recursion without using names, just arguments. The compact horror of this function also illustrates why people prefer programming languages with names. If you're on a desktop machine, you can take a little detour with me. Press F12, and this brings up the JavaScript console. So this lets us enter arbitrary JavaScript, so I can do arithmetic. I can assign variables. I can ask what variables plus arithmetic is equal to. And I can even define functions. I'm going to define a function just by saying x goes to 3 plus x. So x is my input parameter, 3 plus x is the output value. So I've just defined a function there, and I'm going to now call that function with 10, so that's similar to the syntax I'm using here. Define a function and then call it, and I get 13. It's a really weird way to write this. Traditionally, you might say, for example, I'm going to write a function add 3, and it's going to be equal to x goes to 3 plus x. Now I have a function named add3 that I can call with 10. That's the same operation though. It's just in the Lambda calculus style, you define the function and then immediately call it. Here's where it starts to get goofy. I can pass functions to other functions. So for example, I can pass add3 to add3 as a parameter. Now, most of the time this doesn't make any sense, and this particular one didn't make any sense. Add3's job is to take 3 plus whatever the parameter is. The parameter is this function itself, so it took 3 as a string and added the function to 3. That doesn't really make a whole lot of sense, but there are functions for which you might want to pass other functions in. For example, our halts function took another function as a parameter, and then it would do some analysis on that function to figure out what the function is doing, and if it would halt or not. So this is an extremely common operation in Lambda calculus and in functional programming generally. So for example, here we're saying f goes to f of f. Let's try that on this add3. So I'm going to say my parameter is f, and I'm going to call that function with itself as a parameter. So if I pass add3, that does exactly like calling add3 with add3 as a parameter. That wasn't useful for add3. But I can write another function. So for example, this can now take itself, call it me, and now I can do something with myself. In other words, I have a name for myself inside the function, and then I can, for example, recursively call myself. So I'm going to call me of 3, and this actually calls itself successfully one time, and then it tries to call 3, and then 3 the second time around is actually not a function. You can see I'm actually several layers deep into these anonymous functions. Debugging gets to be awful if you don't have names for things, but essentially the Lambda calculus idea is that I'm going to get useful work done by passing functions to functions, and it turns out that's all you need to represent everything in the program. Despite how simple Lambda calculus is, you can still write contradictory self-reference in it, like this. It's line-by-line equivalent to our JavaScript. We take halts as an argument, we do the f goes to f of f trick to get ourselves as an argument, and then we infinite loop or return a constant. Church's Lambda calculus, it's the pure functional style that evolved into Lisp and Scheme and Haskell and the other functional programming languages. It's incredibly powerful. The imperative programming languages like C, Python, JavaScript, they evolved from the Turing Machine, which consists only of a tape and a finite state machine control unit. You don't need functions, variables, or names in a Turing machine either. This is actually a complete JavaScript interpreter for Turing machines. So A is the control unit state table, B is the tape, C is the end state, D is the start state, and E is the position of the head. To be honest, it's awful writing code in either of these minimal languages. They're designed to make proofs easy, not to make programming easy. But both of them support contradictory self-reference, and they're so simple. One of them will work in anything you'd call a programming language. So what that means is, surprisingly, you can't ban this sort of self-reference and still write real programs. What can we do then in a world where it's literally mathematically impossible to tell whether a program is going to stop? Well, when a program stops responding, You close it or wait for it to keep running. That's all we can currently do because there isn't a yes or no answer to the halting problem. It's uncomputable. The bottom line, is there an algorithm for truth? One last word. We said this circuit was banned in combinatorial logic. But in non-combinatorial logic, it's an oscillator circuit. It's useful for generating clock pulses. If you feed a NOT gate into another NOT gate, you get a thing that works a lot like a flip-flop, which is the fundamental operation we use to store data on a computer. In other words, these are really useful circuits. They're just not statically determinate. Self-reference is absolutely everywhere. If I repeat geometry with more geometry, then what I end up with is a fractal. It's still hazy, but I feel like there are huge opportunities to exploit the beyond binary logic of self-referential programs. For example, a self-aware program sounds like clickbait or philosophy, but the halting problem suggests a precise definition of self-awareness, able to recognize your own source code when passed as an argument. If you had a self-aware halts function that could look at the function you're passing it and say, oh, it calls me, and it calls me in such a way that I can't actually give you an answer, that would be a really useful thing. Now, that's not nearly as easy as it sounds, because I could take halts and I could take the JavaScript and use the V8 JavaScript engine and turn it into x86. And I could repeat that sort of layers of obfuscation and translation as many times as I wanted. And a truly self-aware program would have to realize, I see what you did there. That's just me that you're referring to. That's a degree of self-awareness that even humans don't actually possess. If you gave me a scan of my brain, I wouldn't be able to tell you what the heck was happening in there. But I feel like if you had that, suddenly you could actually you could solve the halting problem, right? You could answer the unanswerable, and this would take you beyond algorithms, which sounds like a powerful and interesting thing. It's kind of surprising no one's talking about it. If you enjoyed this video, give me an infinite number of thumbs up. I'm Dr. Lawler from the University of Alaska Fairbanks Computer Science Department.